Hello everyone, let's discuss the topology semester of the Topology and Computability module. First, let's define a topological space. Let X be a non-empty set. A set T of subsets of X is said to be a topology on X if first, X and the empty set belong to T. Second, the union of any finite or infinite number of sets in T belongs to T. Third, the intersection of any two sets in T belongs to T. The pair X with T is called a topological space. Now, let's define the discrete space. Let X be a non-empty set and let T be the collection of all subsets of X. Then T is called the discrete topology on X. The topological space X with T is called a discrete space. Now let's define an indiscrete space. Let X be any non-empty set and let T be the set just containing X and the empty set. Then T is called the indiscrete topology and X with T is said to be an indiscrete space. Then let's give a result for a discrete topology. If X with T is a topological space such that for every X in X, the singleton of the set just containing X is in T, then T is the discrete topology. Following on, let's define open sets. Let X with T be any topological space. Then the members of T are said to be open set. Hence, let's give results for open set. If X with T is any topological space, then first, X and the empty set are open set. Second, the union of any finite or infinite number of open sets is an open set. Third, the intersection of any finite number of open sets is an open set. Next, let's define a closed set. Let X with T be a topological space. A subset S of X is said to be closed in X with T if its complement in X, namely X without S, is open in X with T. Then, let's discuss results for closed sets. If X with T is any topological space, then first, the empty set and X are closed sets. Second, the intersection of any finite or infinite number of closed sets is closed. And third, the union of any finite number of closed sets is a closed set. Now, let's define Clopen Sets. A subset S of a topological space X with T is said to be Clopen if it is both open and closed in X with T. Then, let's define the cofinite topology. Let X be any non-empty set. A topology T on X is the finite-closed topology or the cofinite topology. If the closed subsets of X are X and all finite subsets of X, that is, the open sets are the empty set and all subsets of X which have finite complement. Now, let's give a result for finite closed topologies. Let T be the finite closed topology on a set X. If X has at least 3 distinct Clopen sets, then X is a finite set. Now, let's define the inverse image, also known as the pre-image. Let F be a function from a set X into a set Y. If S is any subset of Y, then the set f to the minus 1 of S is defined by f to the minus 1 of S equal to the set of all X where X is in X and f of S is in S. The subset f to the minus 1 of S of X is said to be the inverse image of S, also known as the pre-image of S. Now, let's give results for inverse images. Let Y with T be a topological space and X a non-empty set. Further, let f be a function from X into Y. Put T1 is equal to the set of all pre-images of S for S in T. Then T1 is a topology on X. Now, let's move on to define a basis. Let X with T be a topological space. A collection B of subsets of X is said to be a basis for the topology T if every open set is a union of members of B. Now, let's define the Euclidean topology on the real numbers. A subset S of the real numbers is said to be open in the Euclidean topology on the real numbers if it has the property that for each X in S there exists A and B in R with A less than B, such that X is in the set from A to B, which is a subset of S. Now, let's give a basis for the Euclidean topology. Let B be the set of all A to B, where A and B are in R, with A less than B. Then B is a basis for the Euclidean topology on R. Now, let's discuss something which is not a basis. Let X be the set ABC and B be the set containing the set of just A, the set of just C, the set of A and B, and the set of B and C. Then B is not a basis for any topology on X. Now let's give a result for bases. Let X be a non-empty set and let B be a collection of subsets of X. Then B is a basis for a topology on X if and only if B has the following properties. First, X is equal to the union over all capital B in B of B. Second, for any B1 and B2 in B, the set B1 intersect B2 is a union of members of B. Now, let's give an example for a basis for a topology on reals. Let B be the collection of all half-open intervals of the form A to B including B, where A is less than B. Then B is a basis for a topology on R, since the union of all members of B and the intersection of any two half-open intervals is a half-open interval. Now, let's give a result for a basis. Let X with T be a topological space. Family B of open subsets of X is a basis for T if and only if for any point X belonging to any open set U there is a capital B in B such that X is in capital B, which is a subset of U. Then let's discuss a relationship between open set and bases. Let B be a basis for a topology T on a set X. Then a subset U of X is open if and only if for each X in U there exists a capital B in B such that X is in capital B, which is a subset of U. Now let's discuss a result for multiple bases. Let B1 and B2 be bases for topologies T1 and T2 respectively on a non-empty set X. Then T1 equals T2 if and only if first, for each capital B in B1 and each X in capital B, there exists a B' in B2 such that X is in B', which is a subset of capital B. Second, for each capital B in B2 and each X in capital B, there exists a B' in B1 such that X is in B', which is a subset of capital B. Now, let's move on to defining a limit point. Let A be a subset of a topological space X with T. A point X in X is said to be a limit point, or accumulation point or cluster point, of A if for every open set U containing X contains a point A different from X. Now, let's relate closed set and limit point. Let A be a subset of a topological space X with T. Then A is closed in X with T if and only if A contains all its limit points. Let A' be the set of all limit points of A. Then A union A' is a closed set. Now, let's define the closure of a set. Let A be a subset of a topological space X with T. Then A union A' consisting of A and all its limit points is called the closure of A and is denoted by A bar. Now, let's define a dense set. Let A be a subset of a topological space X with T. Then A is said to be dense in X, or everywhere dense in X, if A bar equals X. Now, let's give a result for dense set. Let A be a subset of a topological space X with T. Then A is dense in X if and only if every non-empty open subset of X intersects A non-trivially. That is, if U is in T and U does not equal the empty set, then A intersect U does not equal the empty set. Now, let's define neighbourhoods. Let X with T be a topological space, N be a subset of X, and P be a point in N. Then N is said to be a neighbourhood of the point P if there exists an open set U such that P is in U, which is a subset of N. Then let's give a result for neighbourhoods. Let A be a subset of a topological space X with T. A point X in X is a limit point of A if and only if every neighbourhood of X contains a point of A different from X. Also, then the set A is closed if and only if for each X in X without A there is a neighbourhood N of X such that N is a subset of X without A. Further, A is in T if and only if for each point X in A there exists a neighbourhood N of X such that N is a subset of A. Also, A is in T if and only if for each x in A there exists a V in T such that x is in V, which is a subset of A. Now, let's define a connected space. Let X with T be a topological space. Then it is connected if and only if the only Clopen subsets of X are X and the empty set. Now, let's give an important example of a connected space. The topological space R is connected. Now, let's discuss a disconnected set. A topological space X with T is not connected, that is disconnected, if and only if there are non-empty open sets A and B such that A intersect B is empty and A union B is all of X. Then, let's move on to defining the subspace topology. Let Y be a non-empty subset of a topological space X with T. The collection Ty, which is equal to the set of all O intersect Y, where O is in T, of subsets of Y is a topology on Y called the subspace topology, or the relative topology, or the induced topology, or the topology induced on Y by T. The topological space Y with Ty is said to be a subspace of X with T. Now, let's give a result for a subspace topology. Let B be a basis for the topology T on X, and let Y be a subset of X. Then, the collection BY, which is equal to the set of all B intersect Y, where B is in B, is a basis for the topological space Ty on Y. Now, let's define a product topology. Let x1 with t1 up to xn with tn be topological spaces. Then the product topology T on the set x1 times all the way up to xn is a topology having the family O1 times all the way up to On for Oi in Ti for I from 1 to n as a basis. The set x1 times all the way up to xn with the topology T is said to be the product of the spaces x1 with t1 up to xn with tn and is denoted x1 times all the way up to xn with t or x1 with t1 times all the way up to xn with tn. Then let's discuss a result for a product topology. Let x with t1 and y with t2 be topological spaces and let T be the product topology on x times y. Suppose R with t1r and S with t2s are subspaces of x with t1 and y with t2 respectively. Then the product topology on R times S obtained from t1r and t2s is the same as the subspace topology on tr times S on R times S, a subset of x times y. Now let's define a continuous mapping. Let x with t and y with t1 be topological spaces and f a function from x into y. Then f from x with t to y with t1 is said to be a continuous mapping if for each u in t1 the inverse image of u is in t. Hence, let's give a result for continuous mapping. Let f be a mapping of a topological space x with t into a topological space y with t dash. Then the following are equivalent. First, for each u in t dash, the preimage of u is in t. Second, for each a in x and each u in t dash with f of a in u, there exists a v in t such that a is in v and the image of v is in u. Then let's give another result for a continuous mapping. Let f be a function mapping R into itself. Then f is continuous if and only if for each a in R and each open set u containing f of a, there exists an open set v containing a such that f of v is in u. Next, let's relate continuous mappings and closed set. Let x with t and y with t1 be topological spaces. Then f from x with t to y with t1 is continuous if and only if for every closed subset S of y, the preimage of S is a closed subset of X. Then let's discuss a result for continuous mapping. Let x with t, y with t1 and z with t2 be topological spaces. If f from x with t to y with t1 and g from y with t1 to z with t2 are continuous mappings, then the composite function g circ f from x to t to z with t2 is continuous. Then let's relate continuous mappings and induced topologies. Let x with t and y with t1 be topological spaces and let f from x with t to y with t1 be a continuous mapping. Let A be a subset of X and T2 the induced topology on A. Further, let G from A with T2 to Y with T1 be the restriction of f to A. That is, g of x equals f of x for all x in A. Then G is continuous. Now, let's define open and closed mapping. Let x with T and y with T1 be topological spaces, and let f be a mapping from x into y. Then f is said to be an open mapping if for every A in T, f of A is in T1. The mapping f is said to be closed if for every closed set B in x with T, f of B is closed in y with T1. Then let's give a result for product spaces and continuous open map. Let x with T1 up to xn with Tn be topological spaces, and let x1 times all the way up to xn with T be their topological space. For each I from 1 to n, let Pi go from x1 all the way up to xn to xi be the projection mapping. That is, Pi of x1 to xn equals xi for each x1 to xn in x1 times all the way up to xn. Then each Pi is a continuous surjective open mapping. Now, let's discuss a rule for constructing continuous functions. Let X be a topological space. If A is a subspace of X, the inclusion function J from A to X is continuous. Then, let's discuss maps into products. Let f from A to X times y be given by the equation f of A goes to f1 of A, f2 of A. Then f is continuous if and only if the functions f1 from A to X and f2 from A to Y are continuous. The map f1 and f2 are called the coordinate functions of f. Now, let's discuss being homoeomorphic. Let x with T and y with T1 be topological spaces. Then, they are said to be homeomorphic if there exists a function f from x to y which has the following properties. First, f is 1 to 1. That is, f of x1 equaling f of x2 implies x1 equals x2. Second, f is onto. That is, for any y in y, there exists an x and x such that f of y is equal to x. Third, for each u in T1, the pre-image of u is in T. Fourth, for each v in T, the image of v is in T1. Further, the map f is said to be a homeomorphism between x and T and y in T1. We use this notation. Now, let's move on to defining the component. Let x with T be a topological space. Let x be any point in x. The component in x of x, Cx of x, is defined to be the union of all connected subsets of X which contain X. Then, let's discuss a result for component. Let X be any set in a topological space X with T. Then, Cx of X is connected. Then, let's give another result for component. Let A and B be points in a topological space X with T. If there exists a connected set C containing both A and B, then Cx of A equals Cx of B. Next, let's give a result for surjective and continuous map. Let x with T and y with T1 be topological spaces, and let f from x with T to y with T1 be surjective and continuous. If x with T is connected, then y with T1 is also connected. Then let's give a result for connected product spaces. Let x1 with T1 up to xn with Tn be topological spaces. Then the product of all xi with Ti for I from 1 to n is connected if and only if each xiti is connected. Now, let's define a finite subcovering. Let I be a set, and let OI for I and I be a family of open sets in a topological space X with T. Let A be a subset of X with T. Then OI for I and I is said to be an open covering of A if A is a subset of the union over all I and I of OI. A finite subfamily, OI1 up to OIN, of OI for I and I is called a finite subcovering of A if A is a subset of OI1 union all the way up to OIN. Then let's define a compact space. A subset A of a topological space X with T is said to be compact if every open covering of A has a finite subcovering. If the compact subset A equals equals x, then x with t is said to be a compact space. Then let's give a result for continuous surjective maps. Let f from x with t to y with t1 be a continuous surjective map. If x with t is compact, then y with t1 is also compact. Also, note that every closed subset of a compact space is compact. Now, let's state Tychonoff's theorem. If x1 with t1 up to xn with tn are compact spaces, then the product space of the product for xi ti from I equals 1 to n is a compact space. Then, let's state a quotient mapping. Let x with t and y with t1 be topological spaces. Then y with t1 is said to be a quotient space of x with t if there exists a surjective mapping f from x with t to y with t1 with, for each subset u of y, u is in t1 if and only if the pre-image of u is in t. A surjective mapping f with this property is said to be a quotient mapping. Then let's give a result for quotient mapping. Let x with t be any topological space and let tilde be any equivalence relation on x. Let y be the set of all equivalence classes of tilde. We can denote y by x quotient tilde. The natural topology to put on the set y, which equals x quotient tilde, is the quotient topology under the map which identifies the equivalence classes. That is, it maps each equivalence class to a point. And as ever, thank you for watching.